Hi. This demonstration is direct shear testing of granular soil, ASTM D3080. We perform direct shear testing on granular soils such as sands and gravels in order to estimate the shear strength of the material. To perform the test, we use a direct shear machine. This is just one example of a direct shear machine. There are many different manufacturers and many different styles and configurations, but they all basically look the same in terms of the principle of operation. So I want to bring you a little bit closer, and we can take a look at some of the key components of this device. What we have here is a box full of soil. We're going to call that a shear box. I'm going to take a closer look at that in just a minute here. What you do is you take your shear box full of soil and you place it inside this larger box. There's two halves to the shear box, the top half and the bottom half. This is a motor with a screw, and it advances the bottom half at a very, very slow rate on the order of 0.0001 to 0.04 inches per minute. So the bottom half of the box moves, and this larger box moves. You're going to measure that horizontal deformation using a dial gauge here. Here I have an analog dial gauge. You may have a digital dial gauge or a proximeter or LVDT. Here again I have an analog dial gauge. That horizontal reading that you're going to be taking, we're going to refer to that as G sub H. As the screw advances, you have displacement along a shear plane between the top and the bottom. The soil is being sheared. Some of that load is transferred across that shear plane into the top half through this bar and here to a load cell. This happens to be a digital load cell. My display is right here. I'm reading in pounds in this instance. That is the shear force, and we're going to refer to that as F. Now, what you're also looking at is you're also looking at changes in volume or changes in vertical displacement of the top of the specimen to determine whether or not your specimen dilates and contracts. Again, we're going to talk about that later on. In order to measure that, you have a separate dial gauge. This is a vertical dial gauge. Again, you may have a digital dial gauge or LVDT. I just have an analog dial gauge. The reading you're going to be taking off of this dial gauge, we'll refer to that as G sub V. So when you begin running the test, you control the strain rate, again, somewhere between 0.0001 and 0.04 inches per minute. That's going to be your target deformation rate. Most machines have a control system right here that will allow you to do that. You'll be able to quantify that deformation rate using data from this particular gauge here. When you shear, you're going to be applying normal load to the specimen. So what I have here, this is an arm here, and it's connected to a hanger that goes below the instrument to the bottom of the direct shear device itself. Basically what we do is we place weights on that hanger, and that applies normal load. If we take that normal load and divide it by the area of the specimen, we can calculate the normal stress. So we're going to calculate the shear strength of that failure plane as a function of normal stress. As normal stress increases, there's going to be more available shear strength, and we'll end up plotting what we refer to as a Mohr Coulomb failure envelope. So what I want to do now is I want to give you a closer look at what this shear box is and how we put it together and prepare our specimen. This is my shear box. It consists of a top half, a bottom half, 4 separating screws, 2 locking pins. So what you do is you take the top half, place it on the bottom half, you use these locking pins to screw the two halves together while you're assembling the specimen. Once you have these two locking pins tight, you tighten these separating screws to where the tip of the screw is just touching the bottom half. The separating screws pass through the top half, so you tighten them up just so that they're touching the bottom half. Now you're ready to prepare your specimen. For demonstration purposes, we're going to do it like this. I'm going to take a funnel and I'm going to drop the soil through the funnel from a height of about 1 inch. I'm going to move the funnel around as I fill up this hole. In this hole is where our test specimen is going to be. This hole has an area of A. So we'll take some poorly graded sand and we'll very carefully pass it through this funnel, moving the funnel around, because what we're going to want is a specimen which is flat on the top. So that's why we have to move it around. We don't want to just make a big pile. We want to make sure that the soil covers the gap between the top and the bottom half, because that space between the top and the bottom half is where our shear plane is going to develop. And it's important to use some standard method. I just made up this method, dropping the soil from 1 inch, just to provide some uniformity. If you prepare different specimens using different methods and tested them using different normal stresses, and if those specimens had different void ratios, because one maybe you vibrated that specimen and the other one you didn't, you put more energy into preparing one than the other, what would happen is those points would not plot as a straight line on your more Coulomb failure envelope. So it's important to use uniformity, have uniformity in preparing your specimens. So let's go ahead and finish preparing this one. Okay. I've finished preparing my specimen. The surface is relatively flat. You can see I've got quite a bit of sand on the top of my shear box. Hopefully you can do a little bit better in keeping the sand in the shear box maybe than I did. So what you would do then is you would take a loading cap, place it on top of the soil. You would take your shear box and you would place it in your direct shear machine and you would apply your normal load. We'll do that in a little bit here. But once you have that normal load applied, once you've zeroed that vertical deformation gauge and zeroed your horizontal deformation gauge, you're now ready to shear. Almost. But the first thing you need to do, and this is very important, you need to remove these two locking pins. If you don't remove the locking pins and you try to shear the specimen, basically you'll be shearing these locking pins and you may damage or actually even ruin parts of your direct shear system. So I'm removing the locking pins. I'm going to take each of my separating screws and I'm going to turn it a little bit, maybe about a quarter turn. What that does is that separates the top and the bottom halves such that when I shear this, what I'm shearing is the soil and I'm not getting any extra friction as a result of contact between the top and the bottom half. So I'm going to turn these separating screws about a quarter turn. Now I would be ready to perform the test. When you have your shear box in the shear device, you've removed your locking pins, you've turned your separating screws, you're ready to perform the test. The test is going to go like this. The machine itself is going to push on the bottom half of the box at some rate on the order of 0.05 inches per minute, something very slow. As it pushes on the bottom of the box, there's going to be a load cell here that's going to be seated up against the top of the box. So as I push, I'm going to transfer load across that boundary between the top and the half of the box, which is going to eventually be our failure plane. So that load cell is going to measure some shear force, and we'll call that shear force F. And at some point, the shear plane is going to slip. The bottom half will keep moving. The top half will be held fixed by the load cell. Meanwhile, our horizontal deformation indicator is measuring movement of the bottom half of the box. And we'll use this information in order to derive the shear stress at failure along that shear plane there. So let's go ahead and see what this looks like when it's actually in the direct shear machine itself. Now that we've prepared our specimen in the shear box, we're ready to take the shear box and put it into the direct shear device itself. So we put it in here. The first thing that we need to do is we need to make sure that all of the parts that will be moving during the test are seated against one another. Usually there are a couple of screws here that you can turn. Push that shear box in there and get it nice and snug. And then I have a screw over here that I'm going to use to make sure that my load cell, make sure that this rod that's connected to the load cell is seated up against the shear box itself. So I'll get those tight. Now that that's tight, I'm ready to apply my normal load. Of course, there are hangers below the device, which we're going to put dead weights on, and that weight is going to be transferred through this arm to the loading cap. Now, a lot of times you may need a ball bearing or something to place it on top of the loading cap. Let me give you a better look at the hanger so you can see what's going on there. Here's the hanger system that we have below the device. Now, this piece here, this is connected to that arm that will go up through the top of the device and rest on top of the loading cap to provide the normal load. We have two places to hang weights. If you hang weights here, then the weight that you put on there will actually be the normal load. And we're going to refer to this normal load as N. If you want to use larger normal stresses, you can put a weight over here. Here you have about a 10-to-1 mechanical advantage. So you can take the weight that you put on here and you can multiply that by a factor of 10, again, for trying to achieve larger normal stresses. Now, you may also want to add the weight of the loading cap and the ball bearing itself to N to take into account that effect as well. So, I have a weight here. This one is 1.704 pounds. It says so right here on the end. So what I'll do is I'll place that weight. I'll go ahead and use a mechanical advantage. So I would take that weight and I would multiply it by 10. And I would take that product and I would add the weight of the loading cap to that, and that sum would be N, which I would use in order to calculate the normal stress. I would take that sum and I would divide it by the cross-sectional area of the specimen, which we refer to as A, and that quotient would be the normal effective stress for this particular test. I've applied my normal load. Now I need to move my vertical dial gauge in position. And I'll also need to make sure that that dial gauge is 0. Let me go ahead and do that. Okay, the dial gauge is zeroed. I need to zero my horizontal deformation indicator. That dial gauge is zeroed. I want to double check, make sure that all the moving parts are seated against each other. Everything's okay. I can check my display for the shear force and see that I'm at or near 0, so I can go ahead and zero that gauge as well. I'm nearly ready. Remember, I have to take out these pins because we want to shear the soil. We do not want to shear these pins. I remove them. I have to turn each of my separating screws about a quarter of a turn. Now, I'm ready to begin my test. I have this particular machine motor set at a rate of 0.02 inches per minute. That's the change in this gauge as a function of time. I'm going to need to make readings at a frequent enough interval so that if I see an increase increase in shear stress followed by a decrease, I want to capture and be able to define the peak of that curve. So usually a reading about every 0.01 inches on this gauge is adequate. So I'll get my clipboard, and at every 0.01 inches on this gauge, you can convert that into divisions depending on the conversion factor. Oh, by the way, if you have a conversion factor here for this dial gauge, that will be K sub h. And for this dial gauge will be K sub v. F. So, I'm ready. I'm going to turn it on, and here we go. So we've taken our readings at a regular interval. We read each gauge. Maybe we had a couple of lab partners to help us out. We observed the shear force as a function of those readings. Now we have everything we need to reduce the data. Let's go ahead and take a look at that. Now that we have all of our experimental data, we're ready to reduce it. The first thing you need to do is you need to take your horizontal deformation readings, G sub h, and you need to convert them into net horizontal displacement. That's the net displacement between the top and the bottom of the box, and we'll call that delta H. You also need to take your vertical deformation readings, G sub v, and convert that into vertical displacement, delta v. When you make that conversion, it's important to mind whether or not the sign is positive or negative. That's going to determine whether or not the specimen dilated or contracted, and we're going to talk about that in a minute. And you also need to take the force readings. You measured force as a function of deformation. Take those force readings, F, divided by the cross-sectional area of the specimen, A, and calculate the shear stress on that failure plane or on that shear plane at each measurement. And we'll call that shear stress tau. For your particular load that you used, you need to take that load, which is N, and you will maybe or maybe not multiply it by the lever advantage arm, depending on whether or not you had a mechanical advantage. So you have some normal load N, and you'll take that and divide it by A in order to calculate the normal stress, sigma prime. In this case, we refer to it as sigma prime. We're going to assume that there's no pore pressure developing during the shearing, so we'll assume that it's an effective stress. Once you have that, you need to plot the shear stress on that failure plane as a function of the net horizontal displacement, because we need to do this in order to identify the peak shear stress or the shear stress at failure. Now, you're going to have you may have two different types of curves depending on whether or not you have a relatively dense specimen with a relatively low void ratio or a looser specimen with a higher void ratio. When you plot this curve for a dense specimen, you will observe some peak shear stress, which will associate with failure. Once you hit that peak, the shear stress carried by that failure plane is going to drop off to some residual value. If it's a loose specimen, you won't really observe a peak. The shear stress will just gradually increase to some level value out at large deformations. And typically we'll run this test out to a deformation no more than about 1/4 of an inch. If you plotted each of these curves, looking at the shear stress versus the horizontal displacement, it would look something like this. As I mentioned, we need to plot net vertical displacement, delta V, versus net horizontal displacement, delta H, to determine whether or not our soil specimen dilated or contracted. Dense soils with relatively low void ratios tend to increase in volume during shearing. This is referred to as dilation, while loose soils tend to reduce in volume during shearing. This is referred to as contraction. So depending on whether or not your soil is dense or loose, your curve will look like one of these two curves shown here. So again, we use the curves of shear stress as a function of horizontal displacement to identify the shear stress at failure, and we'll refer to that as tau sub f. For the dense specimens that exhibit some peak, we'll just define tau sub f as the peak value. And for the loose specimens that really don't exhibit a peak, we'll just identify tau sub f as the value of shear stress of some large strain, around 1/4 of an inch or maybe 3/10 of an inch, something near the end of the test. So we've run this test using one normal stress, and for that one normal stress, we've come up with one shear stress at failure. We can also refer to that shear stress at failure, tau sub f, as the shear strength. So what we do is we repeat this test over a range of normal stresses. And for each normal stress, we come up with a different value for tau sub f. Now, if we plot tau sub f versus that normal stress, what we obtain is a more Coulomb failure envelope. And that curve will look something like this. The more Coulomb failure envelope allows us to predict the available shear strength as a function of normal stress. On the more Coulomb failure envelope, the friction angle we'll refer to as phi prime, and the cohesion we'll refer to as C prime. So here for the phi and the C parameters, which define that more Coulomb failure envelope, we've put the prime denotation to it, indicate that they're effective strength parameters, again assuming that there's no development of excess pore pressure during shearing. That's it for now. The next test that we're going to run will be unconfined compressive strength testing of cohesive soils. Thanks, we'll see you then.